So my name is Jayanaka Dantanarayana. I'm from University of Michigan and part of the Jaseci research team. So today I'm going to talk about our research project that we started like 2 years ago called MTP, a meaning type language abstraction for AI integrated programming. And this is the team that worked on this research and built the infrastructure for it. So let's start with the basics. So what is an AI integrated program? So when we want to use LLMs in our programs these days, there are two main ways that we do in development. One is to generate code that will be the program. And the other way is we basically have the LLM perform a functionality in your program. For an example would be a software like Cursor or Copilot in your VS Code, just like doing the thing, doing the inference in the back end. You are not interfacing directly with the LLM. You are going through their interface. So that is an AI integrated program. So it's basically a program that interacts with an AI model during runtime, not the code generation way. This is the when I say AI integration, it means it just interacts with the LLM during the runtime. Okay. So as a motivation example, I'm picking this game level generation example. It's a 2D game. Each level is going to be generated by an LLM. It's generating the map of it, and we just play the game. So this, for the map, this is the data structure that represents the map. So we start with the position. We have x, y, a coordinate of integers, and then we have the wall data type, which is start position, end position, both of position type. And then we have map, which is also which has walls. It's a list of walls. Enemies, a list of positions. Player, start position as a position type. And then we have level, which also contains other metadata along with the map object itself. Okay, so this is the representation of the same map we see on the right, and we are writing this function to generate the next level. And what we're trying to do now is, we could have done this traditionally. We can just hard code it, but today's day and age, many people would like to put an LLM in it. So an LLM is going to generate the next level for us, not the code, the level itself. Okay, so how do generally these next level, these functions are being programmed? The de facto state-of-the-art method is prompt engineering. Prompt engineering has been a pain for past 3-4 years. And to show you why it is a pain, so on the right is the code that you need to basically write, implement the functionality of the game level generation pipeline. So you start with a prompt to describe what the LLM should do, and then you need to specify the JSON schema that matches the type that you want to get as the output, and you have to specify that. And then comes the validation part. When it generates the output, you have to make sure that it adheres to the type definition, and then you have to convert it to the proper type and pass it as an output. So that's the entire workflow a prompt engineer should go through, which is additional complexity. Before actually start beginning the developing the code, getting into the actual coding part, you need to go through all of this to get the LLM in it. Okay, so what if I said we can automate everything? If we can automate everything, wouldn't that be nice? So that is what we try to strive for with meaning type programming model. Okay. So when we say meaning type programming model, this entire research stems from one key hypothesis. If a human can interpret your code semantics and identify the developer's intent, an LLM might as well. So LLMs are these days are pretty good at looking at some part of your code and understanding what you actually mean by that code without seeing the entire code itself. So for an example, here we have DOB of type string. You give the date there. And a human reading this would definitely know, okay, DOB, date of birth of string type, or else this function signature right here, French to English. Okay, you're translating from French to English. You have input of string type, output of string type. Okay, a human can understand. So can an LLM. So why do we need to write a prompt for this? We can just use this itself because this embeds the context for the LLM to use. You don't need another prompt to tell this like thing again. So we build this MTP system to extract that semantics that's already embedded as context in your program to generate these prompts. Okay, we start with the actual abstraction itself. We introduce a language abstraction so that a developer can just say to our underlying system, okay, I have this function, use an LLM to do its functionality. Okay, so the abstraction that we introduce is the by keyword. So you have the level by LLM, and the LLM can be any LLM that you already have instantiated in your program, and you just say by LLM, and that signifies our underlying system, okay, this function, this context right here should be used to generate a prompt and do the inference with an LLM and provide the level typed output. And after implementing that, like just writing that as code, we have to extract the semantics or the meaning of that code to actually generate the prompt. We can't just put this code, source code itself, because this is not going to be the only code that's going to be in your program. There's going to be a bunch more. You don't want to put everything to the LLM. So we use a compiler pass to extract the semantic information, and we generate this MTIR, a meaning type intermediate representation. It's basically a subset of a symbol table that contains the information about your types and data structures in your program, which persists in runtime. So we have this MT-Runtime runtime engine, which basically combines this MTIR with the dynamic value bindings, and then generate the prompt, do the LLM inference, and convert the output to the specific type, and do error handling in the same system. So this is the entire workflow of MTP, or meaning type programming model. And let's take the motivation example that we looked at earlier and go through how it flows through our system. Okay, so we have the source code, the same source code. It can be in different files. You may have different modules that also handle other logic in your program. So you don't want to pass everything to an LLM. You need to extract the context that you really need. So you start with, okay, let's look at all of the context out there, because you can't just traverse files. You just need a symbol table like data structure. So we create a semantic registry specifically because we build this on a Python superset. I'll talk about it in a bit at the end. So you extract a semantic registry. It's basically a symbol table like data structure. We use that to you can't like put all of that into a prompt. You need to extract. Okay, we have this by call side here. Let's get only the semantic information that's relevant for that by call side. So we need to identify those semantics. To do that, we basically traverse the semantic registry and collect all the information relevant to the by call side. In this instance, it's a function call. You have the get next level, previous level, the level object. So you basically get, okay, the function name. I have the function name, nice. You have the input names, input argument names, and the types. Okay, now let's find how these data structures look like and collect all that information and create this MTIR, which is a self-contained data structure that persists in the runtime. Now, this MTIR in the runtime, or the call time of that function, is combined with the dynamic variable binding. That's basically the values that lives in your program. You take those values and just build the prompt. So this prompt can be as simple as this, or it can be complicated. It doesn't matter. What we implemented is this simple. In our research, we found that simplicity works better with LLMs than giving complex, larger prompts. So we build this prompt, and you can see we have the values, and the MTIR information is embedded as plain text in the prompt. Like for instance, map object, you give an example about how this map might look like with the types and everything. Okay, yeah, so we generated the prompt, good. Now let's do the inference. So you have the prompt, you do the inference, and you do the output conversion. In this step, you already know what the output type is going to be, and depending on that output type, you can do the validation. If it fails, you can either do an error handling, or in our case, we did a correction loop. It's up to the implementation of this. You can either go with just error handling or a loop that try to correct itself. But if it passes the validation of the type validation, then good. So it passes, and you just return the value that's generated by the LLM as the object. So when you call the function, it looks like calling a normal function. It's not different. I'll show you how the code looks like right now. So for the evaluation of this MTP, we basically picked two different baselines. So LMQL is one of them. They are actually a language, a model query language. That's what LMQL means, and which allows constrained output generation. And this is basically the code for the same get next level function. But you don't need to go through that. We analyze this in the paper. You can have more detailed insights in there. And this is DSPY, another 2024 ICLR paper. They use, they're basically focused more on like prompt optimization optimization framework, but the interface is much cleaner than using prompt engineering. So this is how MTP looks like, or our implementation. So we basically need to import the model, instantiate the model, use the byLLM annotation, and then call the function as a regular function. There's no difference there. Okay, so let's see how do we reduce the developer complexity in terms of AI integration. So we evaluated lines of code modifications or additions required for AI integration, and you can see MTP, the green bar, is low for all of these benchmarks, and it reduces the number of lines of code needed for AI integration by like 10.7 times, and definitely it's a less amount of work for integrating AI into program with MTP. We also do some user study that you can go into in the paper. In addition, we did accuracy evaluations with the LLMs, with different LLMs. There is some extended evaluation in the paper as well, but the key point that I would like to show with this slide is that with these different models, you can see there's a trend, like when you have bigger, better models, the capability of MTP shines. Like you can see from 4 turbo to 4.0, and even here you have 7B, 70B models, it's getting really well. So the key insight that I would say is that LLMs are becoming more capable at deciphering the semantic information embedded in the code itself. So MTP is performing better. So yeah. So to sum up, this is our contribution, our hypothesis, and our contribution is the by language abstraction, MTIR, and MT-Runtime. This is implemented in the Jaseci ecosystem, which is an open source Python superset, which is a type-safe superset of Python. You can check it out. And we built this byLLM plugin to that, which we add the by keyword and everything. You can just visit byLLM.ai, or you can just join our Discord server. Yeah, thank you very much.
All right, thank you. Any questions?
Hi.
Yep.
Great talk. I was curious about prompt injection attacks. So it seems like you're sending a lot of metadata about the program itself to the LLM. Maybe, well, I mean, certainly the LLM provider now has this, but perhaps also the user could somehow, say, like, inject into the prompt something that will then expose the source code of your project to the user. I was curious if you had any thoughts about that.
So, sure. So let's think. That's a really good question. So, yeah, in this case, we are actually providing like semantic information about the code to the LLM. Yes, and in that case, to be honest, like what we're revealing to the LLM is just the type system in your program to give more context to the LLM. We are not like showing the exact code itself. We are not showing any control flow in there. What we are actually showing is just the semantics, the meaning of the code, like what this function name is. So I think in terms of like revealing a lot of sensitive information, we won't be revealing the exact code. We'll be just revealing the context. So I think, I don't think that it can be a problem, but it is definitely something that we should look at and see like whether that's a real problem. Yeah.
Thank you.
Yeah, thank you very much for this question.
Thank you.
Okay, one quick question.
Oh,
Yeah.
okay, I'll try and make it quick. Yeah, so just basically that near the start you said that this is based on the premise that an LLM is quite good at interpreting what code that has been written is supposed to do. We write a function, the LLM is good at understanding what it is that we tried to write, your translation example. But I don't know if I missed something in the framework that you presented here, it just looks at type information.
Yes. Right now, it just so this has been like this paper was in work for like 2 years. This paper and in the state of the artifact that we submit for this paper is like year old. Right now, we additionally provide context like doc strings and other information as well, in addition to the type system. So yeah, we basically reveal how these types look like. So the developer does need to be aware of how to write their code in terms of how to define their data structures that is meaningful for meaningful in the code. Yes.
Okay. Thank you. Yep.